welcome back. In the last video, we saw an example of how to use the method of undetermined coefficients. And this is a way to find particular solutions to your non-homogeneous linear higher order equations. It was fairly straightforward in the last video. The first thing we did was found the complementary solution, and we're going to start the same way on this problem. Y double prime plus 2y prime equals 2x minus 5, 2x plus 5 minus e to the negative 2x. The complementary equation has the characteristic polynomial lambda squared plus 2 lambda equal to 0 gives me two distinct real roots that lambda is 0 or negative 2. So right off the bat, I know that the complementary solution is c1 e to the 0 times x, which is 1, plus c2 e to the negative 2x. What we did from here was we tried to guess what form the particular solution would take on. By the way, the fancy name for that form we choose is called the trial solution. That's where we're at now. We need to pick a trial solution for this problem. In the last example, when my right-hand side was a linear polynomial, we chose a linear polynomial, or a general one, and then determined its undetermined coefficients. Here, I do have another linear polynomial showing up, but I've also got this exponential showing up. And it can be confusing. Should you pick a linear polynomial? Should you pick an exponential? Should you pick some combination of them? Should you avoid both of them? It's a little unclear, and with these guys, that intuition comes with practice. But I want to show you the problem-solving process of trial and error on here. So let's start simple, and let's go with both. Let's say, you know what? I've got a linear polynomial showing up, so I think I've got a linear polynomial in my particular solution. I've also got this e to the negative 2x showing up, so I also think that's part of the solution. Okay. And let's see what happens with this guess. I get that yp prime is equal to a minus 2c e to the negative 2x, and yp double prime is equal to 4 e to the negative 2x. And now I plug that into my differential equation because the particular solution should solve it. I get from my differential equation that yp double prime plus 2yp prime is negative 4c e to the negative 2x plus 2a. But wait a minute, that was supposed to equal 2x plus 5 minus e to the negative 2x. Well, let's try to determine our coefficients from here. Notice that I can build an equation out of these guys, that negative 4c should equal negative 1, or in other words, c is a fourth. And then I can build another equation using my constant terms here. This tells me that 2a should equal 5, and this gives me a equals 5 halves. And now comes the part that maybe some of you with a keener eye have already spotted as an issue with what I have written down. Well, I don't have a linear term up here. I really have 0x. So 2 should equal 0. Uh-oh. Well, that certainly is never going to happen, regardless of which A, B, and C we choose. Not to mention, I didn't even get any information about what B should be. So something went wrong here. Turns out actually a couple of things went wrong here. And I want to show you how to spot each of the mistakes in my trial solution. The first mistake being having an e to the negative 2x term at all. I don't need one because I've already got that piece covered by my complementary solution. There's another mistake in here though, and it's very similar to the one I just pointed out. Pause the video here to see if you can catch it. Ready? The other one is I also already have a constant term in my complementary solution. So I shouldn't have one of those here either. So maybe let's back up. Let's just try AX and see what happens. All right, there we go, cleaned up a little bit. So this time we're going to try not including any of that repetitive information, because the complementary solution's got me covered, right? It's got the constant, it's got the exponential. So let me just worry about the linear piece, and let's see what happens. If I just let yp be a times x, I see that yp prime is just a, and yp double prime is 0. So plugging that into my differential equation, yp double prime plus 2yp prime, that's just 2a. But that's supposed to equal 2x plus 5 minus e to the negative 2x, and shoot! I've got the same type of problem again. This time, because I don't have any linear terms, I get the nonsense that 2 is equal to 0, and I get a second piece of nonsense this time, that negative 1 is equal to 0, since I don't have an exponential term either. So what the heck? It feels like we're stuck at the moment. In the first trial, in trial 1, what we learned was that repeating information from the complementary solution leads to nonsense. So we don't want to repeat terms in YC. But in this example, we saw wholesale leaving out a constant and an exponential from our trial also gave us bad news. So we learned that we don't want to ignore any terms on the right-hand side. How are we supposed to accomplish both of those goals at the same time? Well, let's take some inspiration from what we saw in solving homogeneous equations when I had to repeat roots. Okay, third time's the charm. This time, let's heed both of those warnings we just saw. When I set up yp, my trial solution, I want to be sure, A, that everything in the right-hand side is reflected in my trial, and B, I don't repeat any information given to me by the complementary solution. So, I know for sure I need to have a term with x, right? I need ax. I need a term with b, or excuse me, with a constant. Here's my constant piece. I need an exponential. So here's the issue. The constant term is already taken up by the complementary solution. So is e to the negative 2x. In other words, my particular solution is going to repeat those fundamental solutions. So you might suspect, and in fact we want to do it, we should borrow a page out of the homogeneous solutions handbook, and we should tack on an extra degree of x. It's exactly what we're going to do. Over here, on the exponential term, that's straightforward. If I add an x to b, do you notice now I've kind of lost some information there, because now I only have constant terms, or because it's repeating a constant, I'm only looking at linear pieces. I should look at both linear and quadratic. So when I have a polynomial showing up, I need to repeat or apply that repetition trick on everything. The whole polynomial part of my trial goes up 1 degree. Okay, now we know I should end up with a constant and a linear piece after repeating the information. I should end up with an exponential still after repeating the information. Let's take a look at what happens this time. I need to compute the derivatives. Yp prime is 2ax plus b minus 2cx e to the negative 2x plus c e to the negative 2x by the product rule. Yp double prime then is 2a minus, plus 4cx e to the negative 2x minus 4c e to the negative 2x. Now, we substitute this in to our differential equation. And I'm going to fast forward a bit here to plugging it all in, simplifying it all down, combining my like terms. And I'll see you at the end of that. All right, and wouldn't you know it, all three of our pieces of information we need survived, and none of them give us nonsense. If I compare the linear terms in blue here, by matching their coefficients, it tells me that 2a should equal 2, or in other words, a is 1. If I compare the constant terms here in red, it tells me that a, which I now know is 1, plus 2b should equal 5. That tells me that b equals 2. And finally, if I check in green the exponential terms that survive, I get negative 2c should equal negative 1, or in other words, c should be 1/2. So this determines each of my undetermined coefficients, and that informs my particular solution. But remember, the general solution is the complementary solution plus the particular solution. The complementary solution is c1 plus c2 e to the negative 2x. And now I plug a, b, and c that I just found into my particular solution. A, we determined was 1, x squared, plus b, we determined was 2, x, plus c, which we determined was negative 1/2, x, e to the negative 2x. Notice, for my second order equation, I still have only a 2-parameter family of solutions.